So what we're going to talk about today is a paper from John Ladbury's lab. This was when he was still in England. He has moved to the United States. I might have said Dallas, but he may actually be in Houston. Let's share the screen. Okay, so this is the paper. Thermodynamics of protein ligand interactions and salvation. Insights from ligand design. So, John, I don't know how to describe John. John does sort of what I do, quote unquote. We're sort of biophysical chemists. We're biophysicists. I don't know, and we do these funny overlaps of biochemistry, biophysics, but interact with people and on the clinical side of things, developing drugs and trying to understand the thermodynamics of drug binding, ligand binding, protein-protein interactions, etc. So the first thing to notice is that this the first thing to notice is that all of the data in this paper is isothermal titration calorimetry. They discuss this a little bit in the methods and in the introduction. ITC in principle is, and I'll say this down below when I get to it, ITC in principle is the best way to measure enthalpies and affinities. So where's my tip here? K and delta H. And then from K, you can get delta G, and then from delta G and delta H, you can get delta S. And it tends to have less systematic influences on the data. And so this is sort of an extension of our discussion of Van Hoff plots and doing Van Hoff plots, but it's really a discussion that I didn't emphasize, although it's discussed in Van Holt, on the comparison of Van Hoff analysis with calorimetric measurements, and why one method is intrinsically better than the other method. There are lots of things that can make Van Hoff plots difficult to interpret. And these data tend to be more reliable. Partially it's because they're better quality data usually. I did mention previously when discussing some of the centrifuge, some of the centrifuge data, but also some of the microtubule assembly data, the advantages or difficulties, the advantages of calorimetry and the difficulties of Van Hoff. So what they're doing is they want accurate information on contribution of enthalpy and entropy to free energy of binding. And so they're using published ITC data along with some structural information, which basically means calculating surface areas of ligands. So you need some kind of structural information about the drugs, the ligands, and how they interact with proteins. And so how small molecules, or I'll keep saying drugs, interact with their targets. And then how to extract or interpret the general thermodynamic properties of these ligand protein interactions. And what we're looking for, what they're looking for is trends. They're looking for correlations between enthalpies and entropies and changes in solvation specifically, because solvation historically has been described as one of the big contributors. I'll say this again down below. The simple interpretation is that the overwhelming majority of interactions are dominated by enthalpies, favorable enthalpies. But if you break the data up into synthetic inhibitors and biological ligands, and so what that means is compounds that have been synthesized in a lab for some purpose. There's a whole field of people who do this for studying biological function, structure function, not just people who are making drugs. And then biological ligands, or the other way that we might say this is natural ligands that we happen to find. You get distinct subpopulations. And the synthetic inhibitors, the former, have greater average affinity and more favorable entropy changes upon binding. So that's an observation. The former synthetic inhibitors have greater average affinity because they're making drugs that bind tighter and more favorable entropy. The greatest correlation is found between binding free energy and apolar surface burial. Okay, and this is related in a broad sense. Okay, this gets complicated. I exposed you to the complication last week when we went into all of these other factors. Water's released, you break hydrogen bonds, you bury apolar surface. The water releases entropy, breaking the hydrogen bonds of the water associated with the apolar surface means a reduction in favorable enthalpy, and that explains everything. Well, last week, presumably I began to break that down into no, there's this loss of rotational translational freedom, and there are these other contributions that might be things like conformational changes, reorganization of amino acids, and et cetera, et cetera. So I went into a lot of that. This study expands it even more, and it's asking finer, maybe more solvable questions. They're trying to interpret the data from a large database, and their goal ultimately is to design better drugs and have a systematic set of rules to do that. How do you do that? Okay. All right, and so I won't go through all this other stuff in the abstract right now. Okay, and so at a simple introductory level, what we're trying to do is we're trying to measure and relate structure to binding thermodynamics, and use this information to do more accurate structure-based drug design. There are lots of ways you can talk about this, and some of that actually will come up in one of the student presentations. I think we do the paper by Brad Chairs on intercalation and groove binding drugs, DNA binding drugs. These topics will be revisited. So the simple introduction is that if we measure a binding affinity by ITC, we can then calculate delta G. And the ITC also gives us delta H. So knowing delta G and delta H, we can calculate T delta S. And then we can look at those data and draw some conclusions. Now, you know from what we've talked about that there's something called a heat capacity, which is basically a measure of the change in enthalpy with temperature. It also involves a change in entropy with temperature necessarily. It's 1 over T, the partial of delta S with respect to T. In general, this is not discussed here because the data that is in the literature doesn't always report delta Cp. You have to do measurements at multiple temperatures to get that, and not everybody does in exactly the same way. And this is sort of a deficit, and they mention this down below. Okay. And then they give a simple sort of overview that you should actually understand and be familiar with, because this is basically the Ross and Subramanian statement, although they don't actually reference Ross and Subramanian here. Largely, enthalpic contributions come from van der Waals interactions, hydrogen bonding, and electrostatic complementarity. And entropic contributions involve changes in configurational disorder and in solvation of hydrophobic lipophilic groups upon formation of the complex. Okay, and so this is a similar sort of wordy summary of that table in Ross and Subramanian. And the configurational disorder, we're not going to talk about too explicitly. It basically has to do with how many degrees of freedom there are. It has to do with loss of rotational translational freedom when you bind a ligand. Okay, some of this will come up in the paper that Sarah presents on Monday. But when you fix something to a surface, suddenly a lot of that rotation goes away. A lot of the bulk rotation goes away, but also all of the configurations around bonds sort of get constrained as it sits down in a site. And so that's an entropic term. Okay, and you can do things like constrain bonds, maybe with covalent bridges, so that you don't lose that. And it sits down in the right configuration, but you don't have this unfavorable entropic contribution. And then the salvation and the loss of water upon binding hydrophobic lipophilic groups and burying hydrophobic surface. Okay, and so that's the general sort of overview that you should be familiar with from the multiple times we've talked about this. All right. And then this little bit of introduction, let's see. The goal of prediction of binding affinities from structural information. So that's sort of literally the goal. Here's a protein, here's a ligand. From the structures of those two things, not only do they bind, but how tightly do they bind? And with what enthalpy and what entropy? Can we predict that too? So what are the rules ends up being part of the question. To do that stuff, you need structures, and so to work towards that, you really need a crystal structure of a protein and a structure of a ligand. And what you really need is the complex. So you can see how they sit down on one another. And then maybe that allows you to do that from first principles. That's sort of the pie in the sky goal. Okay, and the medicinal chemists have been trying to do this for a long time. Most drugs are identified accidentally, historically. If I give you this tea made out of this plant, it will cure whatever you have. So, and that discovery process goes back literally thousands of years. We think of it as this odd, indigenous people doing this stuff in the jungle. But it was a very systematic thing that people were doing, certainly dating back to Egyptians, for a long time. We've now refined this into a very sophisticated approach. We think we're getting better at this. A lot of times we get a crystal structure. I can assure you when COVID was discovered and all of the protein sequences were exposed, the first thing that happened was people started predicting protein structures from the sequences. Eventually, we got structures of COVID, but we really needed the structure of the spike protein because that became the obvious target. And then the question was, what can you do to stop that? And all of the antibodies that were made were immediately made against spike protein. And a lot of the structure function things that I'm talking about here are the same, with the caveat that that's protein, an antibody, protein interactions. All right? And so we needed to know something about COVID structure, spike protein structure. And in the early literature, in the early days of the pandemic, there was a lot of work done on that spike protein and expressing spike protein with mutations to understand what structures might actually exist in the surface, and then designing in some way, shape, or form that I'm not going to get into, antibodies that would bind to it and that might inhibit its interaction with its pathway into human cells. Okay, so that it might inhibit the receptor on cell surfaces that it binds to. Okay, so it's a lot of the same features. Okay, and there's a lot of, we didn't know anything. The Chinese hid stuff from us. Bullshit. All right. We actually had the sequence in like December 2019, and people were already predicting structures and already they had antibodies within a month. I can assure you. It took them a year to make them ready to go for clinical trials and to be in the market. Anyway, and so the ITC data is the only technique whereby delta G, delta H, delta S can be accurately determined from a single experiment. And the single experiment literally is, I do one titration experiment and I get delta H, and because it's a titration, I get the transition that occurs and I get K. Boom, one temperature. Okay, and so you need to do more than there's just a one, but literally it's that easy, consequently. Okay, and so ITC experiments produce much more accurate sets of data, and we can use this accurate data set in principle to establish the relationship between structure and thermodynamics. Because that's the challenge here. I have a delta G, I have a delta H, I have a delta S, so what? What does it mean? How do you interpret that? Well, it's enthalpically driven. That's the kind of question that I ask of you. It's entropically driven. It's both. Okay. And what? Well, it must be mostly van der Waals hydrogen bonding, blah, blah, blah. Or it mostly burial of hydrophobic surface. Okay. And so that's where the challenge is. And this is one of those papers. I don't know if this is the best paper out there, but in my mind, it's an informative paper for doing that. So the database that they're talking about is a database that, maybe it says this in the methods. They didn't do this themselves. I think this is part of a larger database that exists out there. And there's data on 254 distinct protein ligand complexes, 405 experiments on 29 proteins and 176 ligands. So some of this stuff is redundant, but they have a lot of data. And so they introduce us to this. Sorry, I'm trying to see the bottom of this slide. Oh, it's right up there where I need it to be. I'm sorry. Never mind. It's here. So they introduced this here, and I wanted to sort of blow this up by plotting minus T delta S versus delta H. In the other plots that we have made, we usually plot delta H versus T delta S or delta S. And it has a slope that I told you recently is the correlation temperature. And then you can interpret that in terms of believability or reliability of the trend. That's usually in one particular case. Ligand binding to tubulin is the example I showed you. What they're doing is they're plotting all of this drug data in this format. If it's negative here, minus T delta S negative, so that would mean a positive delta S is favorable, then this would be favorable below this line. So all the data below this line is entropically favorable. And then all the enthalpy data to the left of this zero line is enthalpically favorable. And then this diagonal here is a diagonal. If you look at the diagonal is where delta H is equal to T delta S. Okay, so the diagonal shows you equal contributions of enthalpy and entropy. If you're below the line, the blue dotted line, then it's entropy dominated. It's favorable primarily from entropy. If you're above the line, it's primarily favorable enthalpically. So what you can see is that of these hundreds of drugs, some of them, most of them are enthalpically favorable. Some of them are entropically favorable. Okay. Some of them are both. Okay. And then they break down the data in terms of, and I think the wording for this is down below, what they call biological, medicinal, other. And so biological, as I said, generally means natural. They found it in nature. They didn't go about making it for some other purpose. Medicinal generally means we made it with the goal of having a drug to treat something. And then other is other kinds of categories that I won't try to get into because I don't entirely understand all of them. And so if you notice, they have lines on here for delta G. So this is the K. And notice this is delta G equals 0. So there better not be any data above here where it's something that has no affinity. All right. And then this goes up by 20 kilojoules. So here's minus 20, minus 40, minus 60, the dotted lines. So this is increasing affinity, moving away from the delta G equals 0. Biological is green, and you'll notice most of the green data is between minus 20 and minus 40. So the biological data tends to bind with weaker affinity to its target. All right. The argument that they make is, and there are a number of things that we'll emphasize, is that this is sort of a feature of natural compounds. The argument is that you don't want it to bind too tightly. You want it to be reversible and regulatable. And so a modest affinity is reasonable, okay? I said to you in medical biochemistry, this is sort of a principle that I emphasized at some point in the enzymes lectures, that if you want to know what the Km for a ligand is to an enzyme, a substrate is to an enzyme, measure its concentration. If you discover that CO2 binds to hemoglobin with a certain affinity, then you will be able to, or to carbonic anhydrase or something, then you will be able to predict within an order of magnitude what the affinity is. Okay, so knowing the bicarb affinity and the CO2 affinity concentrations, those are in the wheelhouse of, and we did some calculations showing that at normal concentration, 13% or something of the ligand was bound, okay? And so that's within the right range. You don't want it to have 0 bound, but you also don't want it to be 100% bound. You want it to be regulatable. And so the right shift, left shift was part of that, all right? Oxygen binding to hemoglobin maybe was a better example, where it's in the range of 20 millimeters of mercury, and that's the close to the oxygen affinity starting in the lungs at 100 and going down into the tissues down around 20. That's sort of the midpoint, and so the oxygen concentration is in the right place. So that's the the logic of the biological molecules. The medicinal compounds are red, and notice not all of them, but most of them are between 40 and 60. They bind tighter. They were designed synthetically in a lab, and the goal was tighter binding. Okay, and so here it is. Okay, the other fall into a weaker affinity as well. Okay, and those actually might be compounds that are part of the medicinal pathway, but they never made it to the clinic. They're just what are called lead compounds. Yeah, this works, but it's not binding tight enough. We have to improve it. And these are the red ones are the ones that have been improved. Okay, and so that's what's in this picture. Most of the drugs are enthalpic. Some of the drugs are entropic. The range of affinities is basically in between -20 and -40 and -60 kilojoules, okay, for free energy. There's a wide range in enthalpy and entropy. Okay, and so you can see that because the enthalpy goes from whatever this is, that looks like about 50, positive 50, to -130. And the entropy term, minus T delta S, goes from 75 to -60 or -70. Wide range, narrow range in delta G. And so we've already talked about that in terms of the delta G is equal to delta H minus T delta S. If those two values are offsetting, you'll end up with a tighter delta G than you will the delta H delta S. So there's a wide range of possibilities, and these natural compounds take full advantage of it. All right. So now the rest of this ends up being a discussion of why and how. Why are these compounds weaker? Why are these compounds tighter? What has been modified to make that change? Does this lead to rules? Does this lead to some understanding that we can use? Okay. And so everything I just said, I think, is sort of discussed in here. Okay, and so part of the discussion that I didn't say, and this is what's going to come up here, the early observations were used to argue that enthalpy entropy compensation is an important feature. Okay, so what that means is that these plots look correlated, that a change in entropy correlates to a change in enthalpy, and this correlation is significant. Okay, and it's part of the mechanism, if you will. And we got into that a little bit when we talked about this in terms of the hydrophobic effect. And that's sort of where this came from. What they're saying here is, and this has become sort of a continuing argument in the field, but this is sort of, I think, the general observation. The early observations were that enthalpy entropy compensation, or that trend, was an important feature. However, it's been dismissed primarily because of the Van Hoff plot data, because you calculate delta S from the delta G, delta H. So it's a calculated value. and therefore it's systematic. All right, and this leads to a propagation of small errors in delta G and large correlations between delta H and delta S. And so it's a simple statistical correlation. Now, I mentioned in my paper, the Vulovic and Correa paper, we discussed that. There's a whole section discussing this very point. And we use the temperature, the compensation temperature, to say, no, 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 for tubulin and for these drugs, this really is predominantly a burial of hydrophobic surface, and therefore it really is the release of water, the loss of hydrogen bonding, and they're necessarily correlated. It is enthalpy entropy compensation. You know, it had to do with the magnitude of delta C being different. The magnitude of delta C being different than the experimental mean. Okay, so I think the compensation temperature was closer to, I don't remember off the top of my head. I think the experimental was, I may have this meant backward. I may just be able to say that. The experimental may be something like 4 degrees, and I'm completely wrong here maybe, but the experimental average is closer to 27 degrees, something like that. Okay, so this was the justification. Here they're arguing, no, 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 this whole diverse family of curves is really just a statistical artifact. And if you wanted to know a lot more about that, you've got to go read the papers from Tom Krug that I reference on this very, the analysis of how you properly analyze Van Hoff data. They're arguing that basically because we're also doing this from ITC experiments, the accuracy there allows us, you know, the statistical argument still applies, and it allows us to be a little more confident in the result. Okay. And so now they define what they mean, and I've already said this, but I'm going to go through it a little bit. Divided the complexes into 3 categories. Native, I said natural, biological interactions. Interactions involving synthetic compounds produced by medicinal chemistry. And others, a category comprising pseudo-substrates and lead compounds. And I already used the term lead compounds. Biological and lead interactions are typically lower affinity. Okay, so those were the blue and the red. No, the blue and the green and the blue. Okay. Lower affinity than the synthetics, which are the red in the 40 to 60, minus 40 to 60 category. All categories have broad distributions of their enthalpic and entropic contributions. I've already said how broad the enthalpies and entropies are relative to the free energy. And the distributions of the T delta S are significantly different between the biological and the synthetic. Native protein ligand interactions are dominantly enthalpically favored. So most of the native compounds are weaker affinity and determined by the enthalpy. Whereas on average, medicinal compounds have equal contributions from enthalpy and entropy. Okay. And so they will make the point, and I'll end up saying it again because it's in the text, and Sarah will make the point on Monday, that when you design drugs to have higher affinity, it turns out that it is easier, the text is right here, physically simply easier to improve T delta S as compared to delta H by chemical modifications. And they discuss why that might be. It has a lot to do with the apolar character of the drug and the binding site, okay? They give the possibility that we just don't know enough about making improvements in enthalpy, and so maybe drug design needs to get better in 10 or 20 or 50 years. We'll have a better idea how to do this. The general problem is, and this is also discussed in my paper, and there's a series of papers you can go read to do this, and I think I said it last week. If I didn't say it, I should have said it. If I bind tighter, so if I improve the enthalpy in some way to bind tighter, then I also constrain the molecule more. So my configurational entropy, my inherent dynamics and motion in the binding site is constrained more. So I've also changed the entropy. And you can't make the affinity tighter without also changing the entropy. And that's sort of the argument that we use to say that's why this is true. There are people who discuss this, and I mentioned before, if you've pre-constrained the drug in solution so that it's no different than when it binds, then maybe that will give you an enthalpic improvement that doesn't have a compensating change in the entropy so that the affinity doesn't change. All right, that's the argument. All right, and so that's, I think Sarah will end up saying something about that next Monday. Okay. The reason for this is thought to be, for the medicinal compounds, is thought to be that the medicinal compounds and the changes that we make are generally to apolar groups. So the lead compounds, and this is discussed in this paper later on in the text, lead compounds often are just polar interactions. What does the active site look like? Where can I make an electrostatic interaction, a hydrogen bond? It binds, look at that, it binds. But the affinity is weak, let's improve it. How do we improve it? We tend to increase the amount of buried apolar surface. So the burial of apolar surface of small ligands is known to be accompanied by a favorable entropic change in the interaction. Okay. In contrast, desolvation of polar groups is enthalpically favorable. Okay. There's a lot more about this that we could talk about, but I won't have, maybe I'll say it when we get to something later in the text. All right. And so this is part of the logic of what explains the clustering of enthalpically, natural compounds are mostly enthalpic and medicinal compounds are both. And so they're arguing that if you increase polar surface area in some way, you will affect the enthalpy. But if you change the thermodynamics of parabeing protein line is thought to affect by the influence of detailed topology of the binding site. Yeah, and so all of this is basically saying what I've already said. It's basically saying that modifying the polar surface is primarily going to modify hydrogen bonding and enthalpic interactions in a simple way. And so what they want to sort of get at is asking the question, I'm having to read all of this to make sure the words out of my mouth make sense, that what are the simple features in terms of apolar polar surface area burial that correlate with enthalpy, entropy, or free energy changes in a way that you can do this in a logical way. Okay. If we make polar changes, what are we mostly going to affect? Enthalpies. If you make apolar surface, what are we mostly going to affect? Entropy. Okay, and so that's what they're basically asking. And this is sort of a question at this point, but I'm jumping ahead. So they then do a systematic analysis of correlation between apolar and polar surface areas, what gets buried, and on the ligand, polar solvent accessible surface of the ligand, and the surface changes accessible surface area due to ligand protein interactions. And what they discover is that the most significant, so there's multiple logics here, and I'm beginning to mix them up on you and on me. How are these correlated with delta G, delta S, and delta H? Most significant correlation coefficients are associated with surface area parameters, particularly those describing the interaction between proteins and ligands. All right, so this is the general result, and I'm sort of starting to impose some specific results. So let me back up to something that I was just doing a few moments ago. I can measure delta G, I can measure delta H, I can calculate delta S. Now I have delta G as a function of ligands. I have delta H and delta S. I can make a plot and I can show you that this set of ligands is mostly enthalpic and this set of ligands is mostly entropic and some ligands are both. What more can I say about that? That's what I was saying up above, right? And I was beginning to make this argument. What can I say? And what they're saying to you is surface area. What's the interaction surface area look like? Later in the text, they will start getting into what's the maximum affinity that I can get given the size of a ligand and the size of a binding site, all right? So how much surface area gets buried? How do proteins and ligands interact? They interact through these weak forces that was in the introduction: hydrogen bonding, electrostatic interactions, van der Waals contacts, burial of hydrophobic surface. But all of that means surface-surface interaction. And so can I calculate surfaces pre and post binding? And can I understand the affinity that comes out of that? And then can I understand and predict the enthalpies and the entropies that come out of that? And that's what this is basically saying. So if we look at the surface area, then we will know something about how they interact. Okay. There's a lot of work that has gone into this over the decades. Okay, this might predate. It's almost. I don't think it almost predates. I think it does predate me going to graduate school. When we get to it later, I'll look up the reference because I'm having trouble finding the reference with a quick look. Calculating surface areas and how we calculate surface areas, what the methodology is, and I get it when I know what I'm looking for. And oh, Richards, it's Fred Richards, that's what it is. So it's reference 51 in this paper, Lee and Richards. The interpretation of protein structures, estimation of static accessibility. How much surface is accessible, okay? And the Fred Richards technique, which is what I'm digressing for, is rolling a ball around the surface of a protein. The ball is the size of a water molecule, and asking how much surface is accessible to a water molecule. Okay, if you look at the surface of a protein, I sort of draw cartoons, right? I draw cartoons, and I mean I might even do this, right? Alpha, beta, alpha, beta. Here's hemoglobin, okay? But it has a structure, and so there's a hemoglobin tetramer. But the surface is actually irregular on some fine level. And so for me to see that, by see I mean identify a place to bind, I have to be able to see the topology of it. And so if you roll a water molecule that's way too big for a water molecule along the surface, then that gives you an idea potentially of how a 1.4 angstrom ball, because that's the approximate size of a water molecule, if you treated it as a sphere, would look like rolling along a surface. There might be finer structure than that, but I can't see it, meaning I can't pick it out and make a hydrogen bond at that level of refinement, all right? And so how do you calculate surface area, accessible surface area? That ASA is used throughout this paper, came from Richards, okay? I said before I was in school, that was 1971. So I was still a junior in college in 1971 when that came out. And that's what they're using here to calculate the available surface area. All right. So I just implied they must have a crystal structure for every target in this paper of both the protein and the ligand. They must know what they look like in solution and bound, and they can calculate how much surface is buried. And then I mentioned in the tubulin paper stuff last week that we have formulas for calculating heat capacity changes based upon how much buried apolar and polar surface there is. Because the heat capacity primarily comes out of release of water and solvation changes. And so if you know how much surface is buried and how much nonpolar surface is buried, then you can sort of calculate the amount of water and you can sort of estimate the heat capacity. And so that's what this is about, all right? Have you noticed that all of this stuff is related and in a very painful way? This is building on concepts, all right? So then they jump to a conclusion. The greatest correlation is that between increased apolar surface area buried, including ligand and protein, upon complex formation, and increasing favorable binding energy. And here's the figure. Okay. Buried apolar surface, okay, and delta G. And what you can see is that the favorability, they're plotting it as minus delta G, so increasing means increasing affinity. And this is how much apolar surface is buried. They describe it down below as reduction in hydrated apolar surface. What they mean by reduction is buried. All right. So the more you buried, the higher the affinity. That's the answer right there. All right. You have to have a lot of interaction surface to have a higher affinity. And that surface has to be apolar. We can go home now. All right. There's a select group here. It must be in the methods. I don't remember how they selected this group of data. Crystal structure certainly would be one of them. Okay, you can see there's different classes from green. Well, the coloring here has nothing to do with the other coloring. The coloring here has to do with the fact that they created a list and they had to color code the list. Okay, and so there it is. All right, and then make that smaller, come back up here. They then talk a little bit about the magnitude of the correlation constant. So a correlation constant of 0.65 is not actually very good. Okay. It's a fairly broad. They have on that figure, there's a 95% confidence interval, but basically it's 0.65. Okay. There's a trend. It's the best trend they have in the data. Okay. If they include if they only look at the ligand burial, how much surface is lost on the ligand that is apolar? The correlation, they don't show that plot here. I don't think it's in a supplement. It's only 0.44. So it's not just how much loss on the ligand, it's both. You've got to include both surfaces in this calculation. Okay. And then they describe the characteristics here. So The least squares fit of the line, da 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 da. The slope is minus 49 joules per mole per square angstrom. Okay. On average, the burial of 20 square angstroms appears to lower delta G by 1 kilojoule. Okay. So they're basically looking at how much surface loss and how much gain in affinity. This lower delta G means increase on negative delta G. How much gain in affinity by how much surface. So they're using 20 square angstroms as sort of a unit. Okay. And then here's the reference to Lee and Richards. This is approximately the same slope as definition of accessible surface area. Okay, and so they're using sort of this throwback to the methodology. Okay. So that ends up being sort of a conclusion that the best correlation has to do with loss of apolar surface upon burial, binding of a ligand, making a complex, and an increase in affinity. Okay. And that's partially why ultimately the observation is that you can improve affinity by changing apolar surface or non-polar surface. They like apolar. Okay. And then they make a discussion here that we won't spend a lot of time on, but this has already been sort of predicted by all kinds of studies, but the studies involve apolar solvents. So if you do experiments in ethanol or dioxane, you can see that there's some change in affinity per buried surface area. And the slope of that line is, let me go back here to make sure I have the slope right. The slope is minus minus 49 joules per mole. Minus 49 joules per mole. I might have had a misplaced kilojoules there. And from this theoretical paper, if you will, because it's more apolar solvents, the number is bigger. It's 92 joules. And then looking at the transfer of hydrophobic amino acids, you get numbers that are approximately 80 to 100 joules. And then looking at data from mutational studies. So what that means is if we mutate residues on the surface near a ligand binding site, how does that affect affinity? And they get a minus 63. Oh no, minus 88. Oh no, the mutational is down here, minus 63. So this estimate from the drugs tends to be a smaller number, is what they're saying, than everything that was preceding it. It's within a factor of quote unquote 2, but it's smaller. Okay. Then they go on and ask, okay, so what about polar? Because we didn't start with polar. Apolar was the best data set. If we go to polar, what we discover is that the polar doesn't have the same impact on the calculation. Okay, if we calculate polar plus apolar burial of surface, the plot doesn't improve at all. That's what they're saying here. They're not showing us the plot. And they're surprised by that. And they're surprised by that because there's data out there that looked at both polar and apolar and said that both of them matter. The heat capacity change result that I mentioned to you before about calculating heat capacities in burial of both apolar and polar surface, and there's some formula that is used to predict this. That formula comes out of these two papers. I think it's both papers, 31 and 32. 31, oh. No, it's the one down below. I'm sorry, I'm misreading this. and heat capacity changes in protein DNA interactions. That's what I'm talking about. It's this reference 3. It's this paper number 3 from Spoler and Record in the early 90s on DNA binding, protein binding to DNA. And that's where a lot of the stuff that I already talked to you about last week came from. How much buried surface is there? Is it polar or apolar? And is there a conformational change that occurs upon binding? And remember, we went over that last week in terms of the conformational changes being the other and calculating how much conformational change there must be. That came out of one of the places that came from was Spoler and Record. There's another paper that is usually discussed, but maybe that's not here, from Kip Murphy's lab in Iowa around the same time. He had a slightly different formula. It was actually Kip Murphy's graduate work with Ernesto Freire. Okay, so to make sense of that, they then plotted the change in polar and the change in apolar surface against the total surface area. Okay, and what they get are these correlation plots. And what you can see is that the trend, total reduction in solvent accessible surface area upon complex formation. What you can see is that the apolar burial has a far bigger impact than the polar. And this entire section is sort of discussing this and sort of a little bit perplexed about what that might mean and why that is and how do they make sense out of it. Because a lot of the literature, protein-protein interactions, suggests that both of them should contribute. But for these drugs, it's primarily the apolar stuff that seems to have the biggest impact, with a fairly high degree of correlation. The correlation coefficients here are 0.93. Oh, is it really only, that's only 0.29? That looks better than 0.29, but okay, I'll take their word for it. The R squared, that's the 0.93. That's the tightness of the plot. 0.29. Okay, it's showing intercepts and it's showing slopes. Okay, and so this surprising result is basically that apolar seems to matter more, which explains the medicinal stuff and the modifications in the medicinal stuff, etc. Okay, but then they discuss in the next section things about the intercepts, and they say that the apolar has a negative intercept, so it actually goes below 0 on this axis, and the polar has a positive intercept, and so consequently, so there's less correlation of the polar than the apolar, and so it suggests that the apolar is not really making a significant contribution to the trend. But then they say, oh, by the way, this does not mean that polar surface area burial is unimportant in binding. In fact, extrapolation of the regression line shows that hypothetically, there is a binding free energy of minus 19 kilojoules associated with ligand binding for the burial of 0 apolar surface. All right. So even in the absence of apolar, we can have a significant binding constant. It just doesn't show up in this plot and in this way of looking at the data, this way of correlating polar and apolar with free energy, polar and apolar with surface area burial. But if you go to the place on the plot where the apolar is 0, you'll still have appreciable energy. And if you go to the place on the plot where the apolar buried surface is 0, then this corresponds to an appreciable amount of polar. Well, am I saying that wrong? Oh no, this is binding energy, this is burial. Binding energy and burial. So if you bury 91 square angstroms, you will get minus 20 kilojoules of affinity. Okay? So now you have to sort of explain that away. Okay, well, why isn't it showing up in the data? All right, and then there's a long discussion here about various features. The thing that I selected out here is the number of possible polar interactions is progressively increased. The ligand would rapidly become much more selective due to increased complexity and making complementarity matches. Okay, and so the argument I think that they're making here is that, well, I missed something down here. Okay, part of the argument so sorry, there's a long development here, and this is sort of where we want to kind of see all of this development. Part of the argument here, and hopefully you've sort of looked at this and you're looking at this and you're extracting it from yourself and you're gonna say something about it that makes this clearer. Part of the argument is that when you increase the amount of polar burial, you necessarily are forcing a hydrogen bond and an electrostatic interaction and a van der Waals contact to be in a very specific place with a very specific distance and a very specific orientation. And as you add more of them, you are constraining where those things can be. Okay, so this is the reference to more selective due to increased complexity of making complementary matches. And that becomes more and more difficult. And so they're arguing that increasing these polar interactions, increasing the selectivity, necessarily brings along baggage. It brings along other features that have to be introduced to deal with how difficult complementarity is. And they say down here below, screening libraries focus on small relative polar molecules will initially optimize the polar interactions and the selectivity. And the increase in apolar surface burial becomes necessary to achieve higher affinity because you sort of run out of options with the polar. The nonpolar is sort of nondescript. It means any burial of nonpolar surface will release water and have a favorable contribution, but it doesn't have directionality and distance constraints the same as polar. Okay, and a lot of this discussion is sort of getting at that in a little more refined way. Okay. I'm going to say something right here about that because there was something else I wanted to say. They've now gone on to trying to predict something about maximum affinity. This was sort of the goal at the beginning. I don't want to get into all of this because I don't think they give us enough information to appreciate it. They mentioned that there's a maximum affinity of around 60 kilojoules that they can see in the data set that has something to do with how much buried surface that there is. But they mentioned here this discussion that the recent trend is that you make larger and more apolar drugs than predicted by Lipinski's rules. So a number of years ago, this group, that's reference 40, oh, it's not even referencing Lipinski's paper here. It's a reference, the influence of drug-like concepts on decision-making in medicinal chemistry. Well, anyway, there was a group, the first author's name was Lipinski. It's interesting that they don't reference it here. It's a reference to another paper that had some rules of how many interactions there should be in a drug. And they basically, what Lipinski did, I think he was at Merck, if I remember right, which is a drug company at the time in New Jersey. It still is in New Jersey mostly. And what he did was they compiled a whole series of drugs from Merck and from another company who I'm forgetting what that company is. They were primarily located in Southern Connecticut. And And they said there were rules, and the rules were things like molecular weight. Drugs can't be too big. And there were rules about polarity. Drugs can't be too soluble or too insoluble. Okay, because if they're too insoluble, they won't get anywhere. And if they're too soluble, they may not get to their target because they're stuck in solution, or they're stuck in a membrane because they're soluble in the membrane. And so they're not available in a drug availability, bioavailability concept. And then there can't be too many polar interactions because, and then there was a series of rules about if you have too many interactions, then there are other consequences that have to do with desolvation of the molecules. And so there were all kinds of rules. They were actually known as the rule of 5. Okay, and so it had something to do with you can't be bigger than 500. You can't have a hydrophobicity bigger than 5. You can't have more than 5. And I can't remember that. Was it 5 polar or, and then the number 10 came in, but that was a multiple of 5 polar interactions, because here they're arguing selectivity and difficulty. There he was arguing you have to desolvate all of those interactions, and the cost of desolvation offset what you gained by making a hydrogen bond. Okay, and so this long discussion here says, well, things are not quite, this is a better understanding than Lipinski. Okay, and then below that they mention this paper by Kausman. And Kausman's the one who sort of set all of this off. He wrote this paper in the 50s. He references the Kausman paper. Okay, so that's 1959. And Kausman's paper was this sort of, let me stand up here and tell you what you're going to find is true about all interactions in protein folding and protein denaturation. Okay, so it's a related field simply because it's thermodynamics. And everything is going to be determined by hydrophobicity, and everything is going to be determined by the hydrophobic effect. That's what Kausman predicted. Okay, and then within 10 years or so, people said, nope, that ain't true. It's not that simple. There's a lot more going on. Kausman's wrong. And so a lot of the concepts came out of this hydrophobicity and burial of hydrophobicity, but then other things contribute, and it's not certainly an absolute rule. And you can see that it's got the water release and ordered water and favorable entropy is all there. No, it's not that simple. Okay, and so they're basically countering what we thought was true. All right. And as I say, within about 10, 15 years, we knew that Kausman was wrong. Although we all know about it and talk about it, if you sort of are up on the thing. Okay, I'm nattering on here. Let's take a 5-minute break, and we'll come back to what we're discussing. Okay, so let's take 5 minutes. It's 11:09, so 11:14. Okay. Okay. Are we back? Okay. So at this point, they then say, okay, let's look a little deeper at this. And they create a series of plots where they look at enthalpy and entropy versus burial of apolar and polar surface. Okay, so I'm sorry. So it's enthalpy versus apolar, entropy versus apolar, enthalpy versus polar, entropy versus polar. Okay, and then they look at free energy versus apolar as a sort of a summary down below. And so the thing that you can tell in this may be faint on your screen. It's faint on my screen. So hopefully you have the paper there. You could be looking at that by yourself. The thing that you notice is the trends are not very good. Okay, there are not very good trends in the data. The data looks sort of scattered. The enthalpy is not really correlated with apolar. The entropy is not correlated with apolar. The enthalpy is not correlated with polar. The entropy is not correlated with polar. All right, and they say up above here, trends in entropy or enthalpy are certainly weaker. The only significant correlation of the structural descriptors, total, apolar, polar, with either enthalpy or entropy, is that between apolar and entropy. And even in this case, the adjusted correlation is only 0.24. Okay. So they're talking about this data right here. All right. And that's a pretty lousy correlation. The others are worse. All right. And so there seems to be no obvious trend in the data. And then this one down below, E, the overall free energy change in apolar surface has the highest degree of correlation with 0.7. And this again is some subset of data that I don't remember where they got it from. Okay. And so the trend is just not there. All right. And the discussion of this, I haven't marked a lot of things here. The discussion of this is basically that there are other things going on that confound the correlation and that make it sort of difficult because enthalpies and entropies, even though the paper begins with saying they're not correlated, so we don't have to worry about enthalpy entropy compensation, there seem to be other factors that are going on that make a tight correlation difficult. And this is sort of the challenge, if you will, of predicting this kind of stuff. We have all kinds of data and all kinds of understanding from other methods that help us to understand this, but it makes it difficult to sort of understand. And part of the issue that they're trying to make is this is a whole conglomeration of drugs and proteins. In each specific case, brings up the possibility of confounding issues that make the enthalpy and the entropy difficult to predict from just buried surface area. And so in the example that I gave you last week, that was all tubulin assembly in the microtubule data. And it was all variations in drugs or ligands or buffer conditions, something, but it was all tubulin assembly. So it was all the tubulin interface coming together, okay? So it was all within a narrow range of potential interactions. A microtubule has a given structure with a particular sort of three-dimensional arrangement. And so it's not surprising that a lot of different conditions assemble things thermodynamically, have the same thermodynamic description. And so they're sort of hand waving a little bit, and that's not fair probably, and saying that, you know, why this doesn't correlate as well, we don't really understand. That's one way of saying it. And so then they get into looking at the thermodynamics of ligand series. And so the idea here is that if we were to compare drugs where we've made small modifications to the same drug that will bind to the same site, but we've made small chemical modifications, and then we look at enthalpy entropy correlations, maybe that is more understandable, and maybe that correlation will make more sense because there are certain commonalities, okay? The binding site on the protein is the same one. We're just modifying the drug. So maybe that will simplify stuff, okay? And that's sort of what this discussion is about. And that's sort of what they're trying to do here into a narrower subset of ligands. They're doing the same sort of thing. They're asking what's the change in enthalpy, and what's the change in entropy, and what's the change in free energy. So remember, this is compared to one another. How are all of these drugs binding to the same site different? Okay, and they're asking questions about correlations and so the trends, they would argue, are a little bit better, but still not great. It's still more complicated. Okay. So we often look at delta deltas. Okay. What's the change in entropy? What's the change in enthalpy? Okay. As a way of sort of asking how big an impact is. Previously, we talked about mutations, and let's look at mutational effects on surface area. If I change the binding of a ligand to a protein, but I mutate, how does that change the affinity? So it's a change in the free energy change. So it's a delta delta. And so they're trying to get at a sort of a better picture of this. You can see the broad range of changes. Notice the same thing is happening. It's a narrower change in free energy, but a wider change in enthalpy and entropy. Okay, so again, these are compensating for one another. It may be statistical, it may not be statistical. And so the free energy is better determined than the enthalpy entropy, but it's still complicated. Okay, it's still complicated and we don't quite know what to do about it. Okay, so the overview of this is that we're trying to do structure, thermodynamics, and relate that to, let's see if I can figure out where this sentence goes here. There we go. Structure thermodynamic data set in general and a structure calorimetric data set in particular is a way of classifying structure, thermodynamic correlations, and as a guide to putting together new understanding, new insights about how drugs work and how we might design better drugs. Okay. When you tell people this is what you're doing, okay? But clinicians would just stare at you, all right? And they would shake their heads and they would say, what the hell are you talking about? All right? You give it to a bunch of people in a clinical trial and it works better. That's how you do it. Okay, well, we can't do clinical trials on 400 molecules in a very quick time frame. And we can't be giving stuff to people just to find out how well this drug is going to work or not going to work. We have to sort of figure stuff out at a much earlier stage of the game. Preclinical is one broad way of saying it. And this is one of the ways that you evaluate stuff earlier in the game. It has to bind to a specific site, so there has to be specificity and selectivity, and there has to be some kind of affinity. We have to be able to deliver it at the right concentration, meaning it has to be soluble, it has to be deliverable. The Lipinski's rules that I told you about a second ago were in principle oral drugs. You could take it with a pill, all right, through the mouth. You didn't have to get IV. All right, that comes up sort of in antibodies and COVID treatment, but generally speaking, you never take antibodies orally. You inject them into a muscle or you take them IV to make sure they get to you. They don't make it through the gut. All right, and ideally you get better delivery IV, but people then have to go to the hospital. And so they would rather take an injection once a month. And then only a fraction of that, it might be 10%, it might be 90%, ends up in the bloodstream and ends up at the site of action. Okay, and so it's similar kinds of questions, right? And we're trying to predict a lot of these features based upon some fundamental thermodynamic properties. And so that's where this is going, okay? And so this restates a lot of what I think I've already been over. And in the end, the abstract even sort of says it better, maybe. Let me go back to the abstract. Okay, so I got that up there. So if you just, I think, look at this. This is partially a summary of what I wanted to say. And so they say in here things that I sort of said, that the prediction tends to work with free energy. The trends work with enthalpy better, maybe. That there is some cancellation of enthalpic and entropic contributions. But generally speaking, so let's read this, thermodynamic changes arising from small differences are relatively large and in general uncorrelated with changes in solvation. So if we looked at the enthalpy and the entropy data, the burials of surface, et cetera, is not explaining it. The trends identified across widely differing proteins are of limited use in explaining or predicting the effects of ligand modifications. A way of summarizing that is it's complicated. It's more complicated than we understand, and we need to do a lot more work. Okay. We know there's an enthalpic and an entropic contribution to binding. We can see correlations between enthalpy and apolar surface area. But beyond that, we really don't quite understand what's going on. We claim that there's no correlation, no enthalpy entropy compensation going on, but apparently small changes that impact enthalpy and entropy compensate and make changes that prevent broad general sets of rules and principles. So the ability for that to be, if that's true, what I just said, if I've summarized that in any reasonable way, then the enthalpic contribution here, the clustering of data, into different regions allow us to say things. Natural compounds bind weaker. Synthetic compounds bind tighter. Synthetic compounds tend to have more entropic contributions, apolar surface burial contributions than natural compounds. Maybe the natural compounds need to be reversible, blah, blah, blah. All of that is sort of correct in a general way. But then when you look deeper, you can get at an enthalpic contribution, maybe. Okay, so a barrier of, you can get an influence of apolar surface on free energy, but the enthalpic entropic contributions become much more difficult to sort out. I have felt for a long time that the general conclusion that enthalpy entropy compensation is statistical is true, quote unquote, because you can show it statistically. But the fact that they're confounding and that they don't explain a lot of things brings back the whole question of, is it because there's a statistical correlation that isn't real, that has no physical basis, or is there a statistical correlation or a confounding correlation that makes it difficult to separate them out? The example that is my favorite example is higher affinity, less dynamic. If delta H, delta G is tighter, and there's more enthalpic interactions, there's less mobility, and therefore there's less favorable entropy. Boom. That's going to happen every time. And you have to sort of work against that. So I wanted to try to make this specific for a moment. If I can find the paper. Ladbury Fire. I think this is the other one that I posted out there. And so this is a paper that Ladbury and Ernesto Freire published. It's a sort of a review-like paper. And this figure is, I think Sarah is going to end up saying a lot of this stuff next week, but this figure is sort of emblematic of it. These are classes of drugs that are used for the same thing, okay? So this class on the left are statins. Okay, I don't expect most of you to know anything about statins. That's Lipitor. That's the one that I'm on. Okay. And then all of these are HIV drugs, small molecule inhibitors of HIV protease. Okay. You do or don't know that when HIV is first replicated, it makes one long transcript. All the proteins are in that piece. And then a protease comes along and cleaves it in particular locations so that this little section now can be translated into a protein. Okay. And if you can inhibit the protease, you shut down the replication, the production of HIV. Okay. The statins, as you should know, inhibit HMG-CoA reductase. And so they all bind to that site relevant to what we're talking about. All right. These are different drugs. The blue box is affinity. So you can see that this class of drugs is built here to have higher affinity. So as you go from one end to the other, higher affinity. This first drug is primarily entropic, and then by the time you get over here, there's a combination of entropic and enthalpic and entropic. And then this family of drugs, it's the same thing. We're getting a slight increase in affinity, but we move from something that's predominantly entropic to something that is predominantly enthalpic with some entropic contributions. Okay. Now, this sequence doesn't seem to match what I was just saying, that we start out with drugs that are predominantly enthalpic, and then we maximize it by increasing the entropy. What Freire has been doing, he's been working with companies and doing calorimetry with companies to sort of simply come up with a slightly broader insight. This is why you're doing papers, so that we can get a broader picture of this. If you want to maximize affinity, you can't do it enthalpically and you can't do it entropically. You've got to do it both ways. You've got to do it both ways. And he even gets more specific, and he argues that it's mostly enthalpic, but there's got to be about 20–30% entropic contributions. And so this has become sort of a rule in the drug design if you're working with the knowledge of Ernesto Freire's theories. All right. And these are sort of the evidence of this is the proof of his theories. There's got to be a mixture of enthalpic and entropic. It can't just be one or the other. Looking at that broad table in the paper, figure 1, there are examples that are entirely entropic. There are examples that are entirely enthalpic. He would argue that those are going to be weaker binding drugs. And this is showing that if you want to maximize affinity, then you really have to have some kind of a mixture, and you have to figure out how to do that in a way that isn't always compensated for, because bad choices will give you compensation that doesn't make the affinity increase. And so that's sort of an extension of what we've been talking about. Okay, I won't get into more of that right here. They get into other kinds of ways of looking at this. And it's interesting that they use non-hydrogen atoms, and they kind of use a rule that has something to do with buried surface as sort of a criteria for this, which is sort of a topic in the previous paper. Close the current tab. I must have written on it, and let's close the, so let's just stop sharing, and if we need to, we can come back to that paper. So talk to me. Questions?
Okay, Dr. Correa, I've got 2 questions. One of them is straightforward, and the other one I'm not sure I'm smart enough to even get it into words to ask. So with the calculation of available surface area,
Yep.
doesn't the resolution of the crystal structure matter?
Well, it's mostly the surface. So accuracy on the surface, it becomes an issue. So yes, you still need some higher resolution structure. You couldn't get away probably. A blob is a blob, you know, and so if it's a 20 or 30 angstroms resolution, you can see a blob, but you will not really be able to calculate.
Yeah, with the rolling of the water molecule, it seems like you'd have to have basically the resolution of a water or close to it.
Yes,
which is,
that's right. So it needs to be in the kind of 1 to 3 angstrom resolution, I think, to be the most accurate.
okay.
So yes, I won't go down the path of my aside. Go ahead.
All right, the complicated question is, their data is showing the lack of an enthalpy entropy compensation. I'm wondering if it kind of comes down to the type of target protein mattering, like whether it's an inhibition of an enzyme versus inhibition of a protein-protein interaction, because ITC probably would miss energy changes in vivo that are happening due to drug interruption of protein-protein interactions. Because
well, now you're changing the question to downstream interaction.
Well, what I'm thinking, the example in my head is trastuzumab inhibiting the dimerization of HER2 or breaking up HER2 dimers with other.
Right, but that's a functional question. That's
okay,
sort of that's the clinician that I mentioned saying, who cares about that?
Oh no, my question is, like, when you break up the dimer though, I mean, then you're losing a whole nother protein and the hydrophobic surface on the second protein and the entropy of solvation of the second protein that wasn't an issue before. And I wonder if that plays in to, like, in vivo plays into the way these energy changes work.
So years ago, my answers are never direct. Years ago in the late 80s, early 90s, medical biochemistry had a graduate student component that was different. Okay, instead of giving you the multiple guess exam that we give now, we used to give separate essay exams for graduate students. And we also had a separate set of lectures for graduate students because we didn't think we were teaching you at the right level. And we still think that to this day. But and I used to give a lecture on a series of papers out of a lab. I know some of this and I'm forgetting something. A lab that was looking at crystal structures of lysozyme. That was the example. There was a whole series of papers. I'm going blank on the guy's name. And the idea was he was doing mutations, and then he was asking what the impact of changing a phenylalanine to a glycine, a phenylalanine to a lysine had on a structure, right? And they were focused initially on what the change in the folding was and what the change in the free energy was, all right? Because they wanted to know, let's home in on this local picture. All right. And the assumption in all of those alternate crystal structures, mutagenized crystal structures, was that there wasn't a global change in the protein. That if this substitution, alanine for something,
Right,
also caused an unfolding of the protein somewhere else, that then changed the stability of the folded protein, then I have no idea what the alanine just did locally. Right. And so that's coupling in a sort of a negative way. The way it was said was it has to be isomorphic. It has to have exactly the same structure except for the local change. And if it's more than a local change, if it's a global change, I'm now trying to still remember the name of the guy, then you can't interpret the data. Okay. And so it becomes a problem. All right. And so when I mentioned the hemoglobin stuff early on, and I think I went over, I referred to this paper a little bit in Med Biochem, but a little bit, 2 months ago, that there's a whole series of mutations in hemoglobin that have different kinds of impacts: higher oxygen affinity, lower oxygen affinity, loss of allosterism, et cetera, et cetera, et cetera. There were some mutations that caused unfolding and loss of tetramer structure. Okay, and that has consequences phenotypically. Those people might die because they don't have a functional allosteric tetramer, et cetera. And so that's a phenotype, that's a structural interpretation, but in terms of thermodynamics, it becomes, I can do all of that, but I now need multiple free energies to interpret that. There's an effect on structure, there's an effect on dimerization, there's an effect on tetramerization, there's an effect on oxygen binding. So you have to talk about all of those at the same time. They're all linked to one another. They're all coupled to one another. Okay. And all of the stuff that I do when I say to you, the esoteric mathematical stuff we do when we derive a partial derivative and we say, what's the change in affinity with respect to oxygen, holding everything else constant. Everything else constant is important because if you don't hold the pH constant and the salt concentration constant and the temperature constant, then this derivative has no meaning. It's actually 6 terms in the total derivative, right? We do all of that, right? We're aware of all of that. And so you have to worry about all of those other contributions. And so what you're saying isn't wrong, that the enthalpy entropy lack of correlation may be because there's so many other things going on that we don't understand and know about. And to simply, if it's statistical, then it's just that delta S is really an artifact. That's really what it means. It's an artifact. All right.
That's what that was really what my question came down to, is if something like that's true and an extra layer of complication plays into the energy exchanges, is the way they designed the experiment, were they more likely to miss entropy versus enthalpy, or the other way around?
So I think 2 years ago, I had people read a paper. I know I had people read a paper because I saw a talk somewhere on this. And so calorimetry does not directly measure entropy. It's you extract it from the data. But if you do the same experiment by NMR, in principle, you can see the drug. And you can see by NMR, depending on what proton or what nitrogen isotope you're looking at, you can see fluctuations, mobility in different residues, right? And so you can actually watch a ligand bind, and then you can watch how flexible it is. And so there's a way of measuring entropy using NMR to do the same kind of experiment. It's a little complicated because you have all of these residencies from the protein and from the drug, and you've got to sort of separate them out. So in principle, if you could directly measure the entropy that way, and that's what this talk and this paper was about, that's potentially another window into it. But the problem partially is that entropy is hard to measure. Entropy is difficult to measure.
That makes sense. I guess it comes down to it's very complicated.
Well, it's certainly very complicated, but we sort of know what's the complication, you know? So configurational entropy, which is sort of what I mentioned, and the fact that every residue has lots of mobility, but when it binds, it loses that mobility. That's understandable and calculatable if you know something about the intrinsic or residual motion of all the molecules. Okay, and so we can comprehend that. And the Freire stuff, I don't remember exactly if what Sarah's going to be talking about is making covalent bonds to reduce that. And then the problem in terms of drug development and application is, okay, let's say this residue is high, these are rotating rapidly, and they have a lot of flexibility. That's their entropic favorable structure. And then they sit down and they're rigid. Well, to fix that, what if I covalently link them together in the right orientation so that they sit down? Okay. The difficulty that comes up, and this is discussed in a lot of the development of these drugs, is now I mutate the protein randomly. And suddenly the active site has a slightly different look to it. This rigid guy no longer can bind, or no longer can bind with high affinity. But this mobile guy is perfectly happy to bind because he's mobile and he can adapt. Okay, so in one of the questions that I gave you as an example, there was a terminology, adaptive binding. All right, and so there's a negative side to too constrained to overcome the entropy loss, but it's no longer adaptable to the mutations. All right, and so the example that we're living through is COVID, and all of the antibodies that no longer work because all the mutations make the affinities, the binding to spike protein, suddenly weaker. They don't work as well against Delta or Omega or whoever else we're fighting against. So it's the same sort of issue. Early on, we wanted to know what the actual structure of spike was in the membrane of the virus, and people figured out ways of mutating that protein. They put in a lot of prolines. They call it a P6 mutant. And they said, aha, this is actually the conformation that we need to bind to. You've seen some literature on different conformations of the spike protein, and that's the target, and that's what we're making antibodies to. But now these mutations in the spike protein are changing the conformation in some way that the antibodies don't work anymore. Or some people's antibodies don't work anymore. You know, so the Moderna antibodies maybe don't work as well, whereas the Eli Lilly antibodies, which you probably know nothing about because nobody talks about them, they also have antibodies that are in the clinics, work a little bit better for whatever random reason. Yeah, it's all there. So it gives us an understanding, a knowledge, a language, a comprehension of how we might think about this.
Great, thank you.
Other questions? So one of the things that I keep saying to you one way or another, I think the way that I started saying it at the beginning was that textbooks are summarized papers. So if what you know is in a book, you don't actually know very much. Okay, my mother used to make fun of me when I was a student, high school, college, you know, because I would sit at a desk and I would work and I would read, I would do my homework, and she would be, you have too much book learning. You don't have enough common sense. You need less book learning and more common sense. Okay. My father's vision of that was that I need to go in the military, grow up and be a man, sort of thing. That was, by the way, during the Vietnam War. So you don't know a lot if you know what's in a textbook. There are exceptions in the sense that there are textbooks out there that are incredibly fundamental and they really do teach you the guts of a topic. That's not true of biochemistry and molecular biology. There is so much omission in biochemistry and molecular biology books, it's disgusting. But the problem is that we know so much, it's hard to get it all into one book. Okay. But now I'm saying you gotta read papers. Well, here's the caveat. Every time I reference a reference to a section in the paper, in the text, you also have to read those papers to understand where that came from. And I was trying to give you some insight into where the Lipinski reference came from, okay, and where the other references came from in that regard. Okay, and I'm looking here to see other papers that I could have been giving you that I could have done that. And then when you read those papers, guess what? There are more papers that you have to read to understand what the point was. There's a sentence here, a paragraph here that's making some point about statistical artifacts, and it's this Krug paper, except it's not one paper. That paper is actually here in this reference list, but there's actually 3 of them. All right. And so you've got to read all of them, or you've got to have some comprehension of where they came from. You must do what I'm telling you to do. You have to do this. But in your area, this is basically what you have to do. Somebody taught me how to run a gel, therefore I know how to run a gel. No, you don't. You don't know a damn thing about gels. Okay. Maybe you know how to run a gel repetitively, and maybe you know how to make it gel correctly, or quite bluntly, I know none of you actually make gels. You all buy gels and you use the gel you buy. Okay. And when it doesn't work, you don't understand why it doesn't work. In my lab, I gave up on purchased gels immediately because it just didn't work as well. We had to make them ourselves. We found that out pretty early. We had to make them ourselves. Okay. But even that isn't enough. Where does it come from? Okay. Where does it come from? A friend of mine who just passed away from long COVID, actually, he caught COVID in New York early in the pandemic. And Ned was, well, when he died, he was 76. So he was already old and he already had health problems, but it took him a couple of years to die from whatever he was suffering from. But I can remember a story years ago where Ned was complaining about a student who was getting ready to graduate and he couldn't reproduce an experiment. And he couldn't reproduce an experiment because he couldn't make a gel. His gels weren't polymerizing. And he didn't understand why his gels wouldn't polymerize, and he couldn't solve the problem. And it turned out, none of you make gels, so you don't know what I'm about to say to you, but it turned out that he used to run gels every day. And so he would make up a solution at the beginning of the week and used it all week, and it worked. But later he's trying to reproduce something, and he's trying to use the same pre-made solution, and it no longer works because it's weeks between experiments. And what he didn't know was that this stuff, it's ammonium persulfate, which is used as a catalyst in making polyacrylamide gel, goes bad in water. And if you wait 2 weeks, 3 weeks, a month, it doesn't work, and you can't polymerize acrylamide, and you can't make a gel. And both Ned and I were shaking our heads going, because he didn't actually understand how polyacrylamide polymerizes. He didn't actually know the chemistry. He knew how to make a gel, but he didn't understand what every individual component did in the process of making the gel. And it's that sort of way, you know, we seem unreasonable, these professors who stand up here pontificating to you. But you have to have some sort of clock, some sort of gauge as to, do I know what I'm doing? Do I understand what I'm doing? Do I appreciate what I'm doing? And could I do it on my own? Do I have an idea that I'm going to go that way because I have an idea, as opposed to I'm following the path that I've been set down and this is what I'm doing? Okay, so I understand what happens in this. I've been through what you're going through. But you have to have this notion that there is no limit. There is absolutely no limit to your capacity. I'm almost being positive now. I'm almost being positive. There's no limit to your capacity. And the biggest detriment to that capacity is not doing the extra step. It's not understanding every step that you do. Okay? It's not putting in the time and the effort. And I know you guys have put in a huge amount of time and a huge amount of effort this semester. But it doesn't end and it doesn't stop. It just goes like that. There's more to know, there's more to do, there's more to understand, there's more to comprehend. And the bad part of this is, as you've discovered this semester, is I expect you to remember 6th grade, and I expect you to remember high school, and I expect you to remember college. I expect you to remember all that stuff because we can't move forward without it, but I don't have time to teach it, or I don't make the time to teach it. Apparently maybe I could do more, but there it is. Okay. So if there's nothing else to be said about this, read a lot. That's all you can do. Read a lot. I usually travel with an iPad along with my phone, along with a computer, depending on what it is I'm reading and what it is I'm trying to do and what's the best device for the reading that I'm doing. I also still carry paper. So I also carry paper, and I have all of those at my disposal sitting in my silly airplane seat as I'm reading and marking things on an iPad, et cetera, et cetera. Vacations are not really vacations. They're opportunities to do things in a pleasant environment. All right. So Sarah's going at 10 o'clock on Monday. And Lindsay is going at 11 o'clock on Monday. Okay. And then on that day, we will assign the people who are talking on Tuesday and on Wednesday. So you have to sort of be prepared to step up. Or I'm going to be rolling dice again. Okay. And on Tuesday, we'll try to get 3 people in if we can. And I said 10 and 11, but if Sarah finishes in 30 minutes, as I said, then Lindsay will go at 10:30, quarter to 11. Okay. And then the same thing will happen Tuesday, and the same thing will happen Wednesday. Okay. Any more questions? Any more comments? All right. Bye. Have a nice day.
Thank you, Dr. Correa.
You're
Thanks,
welcome.
Yeah.
Thank you.